Hey everybody, this is Larry. This is me going over Q4 of the weekly contest 444 minimum pair removal to sort away 2. Hit the like button, the subscribe button, join me on Discord. Let me know what you think about this one. I think there are a lot of ways to do this one. I think I've seen people talk about using like segment trees and segments and union find to kind of group the things. I think those are all reasonable ideas, by the way, as long as you get it working, of course. But the way that I end up doing it was the first idea that came to my head. Which is to use a linked list. I know. It doesn't really come up that often, only because I feel like every time you want to use a linked list, very similar things you can do with like maybe union find or something like that, where you just because I think union find on in a way is an interesting idea that because you want to use a linked list when you're like joining adjacent elements. Right, and as a result, if you're joining adjacent elements, union find is probably fine with that. So I don't know, but it's not. It's just a small implementation detail, if you ask me. I think yeah. So once you kind of realize that you need a linked list, or at least that's what I did anyway. I think everything kind of fell into place. I think the other second observation that you need to make is the second hard part is where is it? Yeah. Oh. To check whether the array is non-decreasing or sorted, right? And the way that I did this is actually by keeping track of, there's an invariant, right? Which is that, or there's a property maybe invariant is not quite the right word, but it's a property, right? Where, okay, so I count the number of numbers that where a pair of them, if you want to say, is out of order, right? And the thing is that the out of orderness, if you want to call it that, and there's probably an actual mathematical term which this isn't so whatever, but I don't know it right now. Yeah, this out of orderness or is local, right? And what I mean by local is that if you update one number at the end, you can only affect the adjacent elements out of orderness, right? Like if you update the last element, the first element is not going to be affected at all because, you know, unless it's next to each other or whatever. But you get my idea. So with that, I just have to keep track. That said, with all these ideas in mind, it's definitely very easy to, you know, now it becomes an implementation problem, but it's also very easy to kind of be like, oh, I got the idea. The implementation should be fine, right? And it kind of could be. I think for me, it's very methodical. But it's definitely very tricky to be precise, and there are a lot of edge cases if you're not careful. And that's the hard part about this. But I think the way that I always think about these things is that instead of thinking about things as one operation necessarily, I think of it as two operations maybe. In this case, two is fine, which is, well, maybe more actually. But I'm going to say, right? Like I treat it as removing two elements and then adding one element back in, right? Like one removal, or it's like two removal, one addition, right? And I think that allows me to kind of preserve the state in which or the invariant is held. And we'll go over what I mean by that as we go over the solution now, right? So I have a node class and I have a sorted list. The sorted list, I guess I didn't really talk about this, is for the heap. I mean, you keep on trying to find the min, so you want a heap. That's really all I had for it. Of course, it's easier said than done because you know you're moving numbers and updating numbers around and stuff like that. But we'll go over it, right? Like I mean, you know, I actually ended up taking about half an hour on this one and made one wrong answer. What did I make a wrong answer on? Huh? I forgot already, honestly. Oh, I remember because yeah. I had a really bad sentinel value for the root node, which I counted an extra out of orderness, if you want to call it that, and it just never terminated as a result. That was a silly mistake again. But yeah, let's go over the code. We have a linked list class, and if you could build your own, why not make it a dumply linked list? And so I did. I did a next and a prev, and yeah, I even keep track of the index and the value. The reason why I keep track of the value is because that is the value, right? And the index is so that I could do lookup things very quickly. I actually don't know if I ever need it. I guess I kind of did. it's what I do to kind of look back up on the heap is why I have this. But yeah, from the heap, because the reason why I don't use the actual heap and use sorted list for this is that we need removal on the heaps, and we'll go over that when we go over there. But that's kind of the reason why. But yeah, okay. So the first thing that I did is that I started with lookup, like I said. So let me actually annotate this. So lookup gives maps an index to the node, right? So then now if we're having an index, we have the node, and we have the index as almost like a key to the original. It's just a key to a node, right? And I kind of it's just mapped to the original number list, right? So yeah, I start on a root with a negative infinity. I had this as -1, and because the input could have negative numbers, that was my mistake, because then now it just kind of is invertedness. But here I keep track of total, and oh yeah, the other thing is ops is just the result, the number of operations we did, right? So yeah, that's the result, and total is total number of orderness. I mean, I don't know. Like I said, naming is a little bit tough. Maybe there's a mathematical. There probably is a mathematical term. I was thinking about inversions, but I think inversions is not quite precise because it's actually like a pairwise thing. But yeah, maybe you can use it. I don't know actually. But yeah, so here we construct a node for each index. You know, index and the nums, right? And this is just doubly linked list stuff. Why not, right? So next is the new node. We set the previous back to the current node, and then here I keep track of the out of orderness, right? So if the current value is greater than the next value, well, now we have one number that's out of order, right? And then we just move to the next, and then move the current to the next element, which is the node we just created. So then now we update the lookup table to from index to current, and then we also will update the heap, right? So this is the heap. So we update, well in this case it's create more than update, but create the heap with the sums of adjacent elements, right? It is what it sounds like. We have a sorted list. We start at the root, yeah, and then for every pairs of numbers we just add the sum in the sorted list, and then we have the left index and the right index. I don't think actually I needed both the left and the right, but maybe, I mean, it helped a little bit with debugging, but I don't think it's necessary per se, but I just kind of put it on there. It's not that big of a space issue. And I just moved to the next. And this is just to populate the heap, right? And then next, well, total is the number of total, disorderness or whatever I called it, out of orderness. So while that's greater than 0, we keep looping. And when total is 0, 0, that means that no index is out of loop, right? So then now we kind of just keep track of a few things, right? So we look at the beginning of the heap, and then now we remove things from the heap. Well, first we remove the top of the list, right? Yeah. And here we have the left node and the right node. I don't think, like I said, I don't think I need the right node explicitly. You could have written right node should, if the invariant holds, then it's something like this anyway. But I think it's just, I don't know. Maybe I could have asserted it. It's just something that I did, and you didn't need it because it's implicit. But yeah, once we remove this heap, we have to remove other things from the heap, right? Which is that, yeah. Huh, did I forget? I guess I lied on this one a little bit. Because I did separate them out. I think, yeah, so I did lie a little bit. But yeah, you want to remove things on the heap. And what I mean by that is that I update the previous sum by kind of doing this thing. But let me rewrite this, right? What I want, and let me move this up for a second. And yeah, what I want is actually, I want if left node dot previous is not equal to the root, then now we remove, yeah, left node dot value plus left node dot previous dot value, right? And then that node is going to be left node dot left or dot previous of index and left node dot index, right? So I want to kind of put it's what I have here originally, but I think now it's more precise in the sense that I mean, I know that the order doesn't matter, but it also allows us to kind of think about these operations separately, right? So here we're still removing things from the heap. And now we know that the and you could kind of think of the array as kind of like this, right? Like if you have, it doesn't really matter the array, but let's say you remove the 2 and the 3, right? Because that's all we want to do for now. We want to remove the 2 and the 3. Well, we removed the 2 from and the 3 from the heap, but that means that we also remove the 5 and the 2 thing from the heap, which is what we have here, right? And we also want to remove the 3, 1 from the heap, which is what we have here, right? Hopefully the code is self-documenting enough that I don't have to like go through it, but yeah, it's just the total, the index of the left node and the index of the right node of that segment, right? If you want to think about it as segments, which I didn't. But also as a result, yeah, like we did 3 changes, right? So we did yeah, this one with the 2 and the 3, we did this one with 3 and the 1, and we did this one with 5 to the 2, or up to 3 changes because it depends on whether they're on the left boundary or the right boundary. But as a result, the orderness can change 3 times, so we have 3 things. So we check whether, okay, well, we remove this, so we check whether it gives a minus, plus or minus 1, and then we check the left boundary, whether that changed, and then we check the right boundary, whether that changed. I think if you really want to be precise, technically, if you want to really say that you remove this, you want to say that, okay, well, check whether 5 is equal to 1 and then add the totalness. But I think for now, I'm happy with leaving it empty. So maybe I lied about it being very precise. But still, yeah, but this assumes that in the whatever you check on 5 and 1 will get cancelled out by the new number that we insert in the middle. I don't know, maybe it's less thingy, right? Anyway, as a result, yeah, and then we're still removing. Maybe I guess this is actually here, right? And then now here we just get the sum, right? So we combine the 2 nodes into 1 node. I kind of debated creating a new node, but I don't know. I don't think it matters that much. I just had to update the index, but I was like, maybe I didn't need to, because then now you take advantage of the left node index. Like if you create a new node, you just have to update the index. That's it. There's no nuance, or it's not that nuanced. It's just that I didn't choose to. But yeah, and then now we update. Yeah, combine the 2 nodes into 1 node. Yeah, I did this. The reason why I kind of write that is that technically, maybe it's a little bit cleaner if I separate them out. Which is that, okay, well, we updated we combined the 2 left nodes, so then now we have to update the right nodes next previous to point back to kind of, and that's what this is for, right? We just have to point the node back in, and that's it. Pretty straightforward in theory, right? So we add the sum together, but then now we have to update heap for the 2 boundaries, right? In this case, it's not quite boundaries per se, right? Because if you kind of think about the thing we had with the, was it 5, 2, 3, 1 or something like that, right? If you update these 2, right? Well, only 2 heap entries you have to well, yeah, you only have to update 2 heap entries, right? You have to update this one, or well, okay, maybe another way to phrase it is that, okay, you went from here, now your new thing is going to be here, right? Where now you have a 5 instead. So then now you have to and here's the last node that you turn. So then now you have 2 updates to the heap. You have these two elements here and these 2 elements here, right? So that's 2 updates, and that's basically it, right? So you update the right side where you have the left node, and I would left node is none. Maybe that's a little bit confusing looking at here. We already update left node, so technically this part will be left node dot next is not none, right? And you just update the left node with its left node dot next. Yeah, keep in mind that, you know, we didn't replace left node, we just update the next pointer. And here the previous, if it's not equal to root, same thing, we update the root, and that's it. And then now we update the out of order of orderness, right? And this is the same thing as here, right? So now we update it to here. So now we have to update whether this is in order or out of order, and same thing here. And we keep the signs and even the, you know, everything consistent. So then we kind of add and subtract. And of course, like I said, I think one thing that I tried to do when I was kind of doing these problems back in the day and wasn't clear about was that I would, instead of having like these things where I break them apart into two different operations, I would try to think of like, okay, well, if this and that and then this, and then you end up having like a lot of if statements just to prevent, like, you know, like maybe if there's a case in which, you know, if left of previous is root, because you can reduce these two cases into like one case kind of, but not actually, because, you know, because you end up with like more if statements anyway. But here, at least it lets me kind of audit every step of the way, right? Because what I mean by that is that you can actually write this as like if left node the previous is now you go to root, then now we check if left node dot previous of value, right, and left node dot value is greater than left node dot next dot value or something like this. I mean, it's not quite that because you have to update next first, which we haven't done. But like if you kind of rewrite the code in that way, then we know that, well, in this case, the delta didn't change. So you would actually write like, you wouldn't write this, but that's kind of your logic, right? You would skip this. So then now you would maybe write, okay, well, if this doesn't do anything, then you go, okay, well, if this is the case and this is the case, maybe you just like and then else, if like maybe you have someone like this, and you know, I mean, I'm not saying that that's what you would have done, but that's what I would have done in my past to kind of get the deltas of the total. But when in reality, what I like about this is that we don't have to think about all the possibilities of these states before and after. We just have to think about, when breaking apart, the before and after of two parts sum up to the right answer, and also they're much easier, right, with respect to kind of just keeping it total. And that's why I kind of want to talk about it like this, is that then now, yeah, the code is just much cleaner to write, and more importantly, much easier to debug as well, right? When you kind of inevitably, I actually didn't make a mistake here, I don't think, at least not for this, but, you know, and you kind of saw a couple of things that I kind of even did before I kind of cleaned this up here, with having like keeping track of the previous node and then adding it that way, but it wasn't necessary. So yeah, and that's pretty much it. So after we kind of update our orderness, given these new nodes, we increase the operation, we print for when I still need to debug, and then we just yeah, return operations. Let me double check. I did make some changes, so I want to make sure that I'm not lying to you, and make sure that it's still accepted. Should be okay, but yeah. So what's the complexity here, right? Well, we have a heap, and we are a sort list. As I mentioned, and I don't think I mentioned this one, but yeah, given that n is n elements, remember that every time this loop runs, you combine two elements into one, which means that you reduce the number of elements by one. So that means that this loop will be at most n times, right? And here we have a lot of heap operations, but they're all log n. So maybe we do at most 5 operations, but that's still log n, right? And that's going to be n log n in total. And that's it. That's all I have for this one. Let's go over, let's kind of do a quick stroll of the code. We have the node. We have the setup into the linked list. We have the setup into the heap. And yeah, forgive me if I didn't go deeply into linked list or node or heap or anything like that. This is a Q4, so I will just assume that you are familiar with these basics. So yeah, but yeah. And then here we do the removal. And here we combine them to one node, and then we update the heap and the boundaries and add them. And that's it. That's all I have for this one. Let me know what you think. Thanks for watching. And yeah, you could watch me solve it live during the contest now. Okay, let's look at Q4. All right, minimum pair removal to sort arrays 2. All right. Adjacent pair. Oh, is this the Q1? What was the difference again? Let's see. I guess it's the same, except for prior to constraints. So you 10 to the 5th. So you can't really do it anymore. Okay, what are we doing then, right? I mean, it should be like a heap E solution. But how much time do I have? 46 minutes. Should be able to get it, probably, possibly. I don't know anymore. I'm so confident, and yet I suck, so... Okay. So there's no choice. We have to do it. So we have a sorted list. So what happens? I mean, just simulation. It shouldn't be that bad, right? Why is this hard? I'm trying to think. I mean, the reason is because you have to get the index very quickly, right? And then keep on doing it. Okay. But otherwise, it's just implementing a linked list. I guess that's the thing that maybe people don't think about, right? What's it called? Man. Yeah, okay, right. Yeah, maybe. I was debating singular or whatever, and I was like, it's fine. Just make it, you know, why are you making it harder for yourself? Make it a whatever. Okay, right? So then now we want to say, okay, let's just convert it to a list, right? So root is equal to node. We have a sentinel, and then for x and nums, yeah, how do I want to write this? Okay, so maybe I have self.index is equal to index, right? Something like that. I don't know if this is quite right, but that's fine. 46 minutes. I'm confident we could get this. It's just that I think the insight is just the linked list part, and it being annoying, but and everything is in a heap probably, because it only affects 2 numbers, right? So yeah, and we could use sorted list as a heap because I'm too lazy to do a lazy heap. Lazy to do a lazy heap. Okay, yeah. Yeah. So okay, current.next is equal to node of index and x, right? And then current is equal to current.next. And then current.previous. Oh man, I messed that up. Okay, fine. .next .previous is equal to current. Okay, and then now we are good, right? Yeah. And then now we actually want to put everything in a list. We're going to lie and say it's a heap, but okay. And then what? Yeah, and then we just go through the entire things, right? So current is equal to root. We want to insert while current.next is not none, current is equal to current.next. Otherwise, we just want to update. Actually, we could use current now, right? Because it is a doubly linked list, so we don't need to do the thingy. And current.value plus, I guess we do need current.next for this particular one, but not current.next.value, right? So we want to add. Okay, so we want to. This is a min, right? Min sum. Okay, so we want to min on this. And then we want to store the index of current.index, right? And I think one thing that I did forget is have a lookup table. So here, I did mean to do this, but I just forgot. So lookup of index is equal to current. Yes, I think so. Yeah, because current.next is a new node. Okay. Right. Okay, and okay, so we go through it, and then now we have to do the sorted thing, right? That part actually I didn't think about. How do you know if the list is sorted? Okay, this part I didn't think about, honestly. Well, nothing changed about the entire state, so you have to check once in the beginning, of course. If there is sorted, so so where is it not sorted? So okay, if you replace the minimum sum, what happens? That means that okay, so the number of not inversions but adjacent inversions, right? And then we have to do some math on that. I guess that's fine, right? Maybe. I think that's probably the idea, but it's still very annoying to do. I mean, I don't think there's anything conceptually hard. It's just I worry about all the bookkeeping. But yeah, okay, fine, right? So then now, I guess it's just the sum of. Yeah, I guess it's just keeping track, right? So okay, so total total inversion maybe. It's not inversions. Inversions mean something else, but like, you know, whatever, just go total then. Then now, if, and I'm intentionally being lazy about this, is that, okay, right? So, well, I'm intentionally double counting about this. So if, so this is before. So if current dot value is greater than current dot next dot value, then maybe I'm not, maybe it's fine, then total increment by 1, right? Because we want to treat it as yeah, this is so annoying to double check. Okay, I mean, I think this is fine by itself, honestly. And then we just have to keep track, which is not easy. I think I expect many wrong answers, honestly. But okay, so we put everything in the heap, right? Okay, so then now, yeah, while total is greater than 0, right? So we get the first, so that's going to be I mean, this is I feel like I'm trying to figure out like how I would remove old ones. I said that I wouldn't remove old ones. Actually, I guess that's fine. Maybe that's fine. Yeah. Okay. So yeah, new x is equal to new x, the index is equal to h sub 0, right? And then h dot remove new x index, whatever, right? But then now we have this new x and an index, and what are we trying to do? Right, so now we want to remove index and index plus 1, right? We removed it from the heap. Well, we moved this pair from the heap, but we also want to remove from the heap the one that for the, and it's not index plus 1 because we're trying to keep the original index just for whatever purposes. It's just that it's left right, so okay, current dot next dot index, we gotta do that, right? So here maybe it's left index, right index, right? And we can remove that, but then now we have to remove the stuff in which the right index is the new index, right? And we can find the math for that probably, but it's easier to just have a lookup table, maybe. Some lookup. And this is an annoying problem. We have 35 minutes. It's spent 10 minutes already, so I mean it's probably fine, but so this is going to be the left. No, I mean it's fine. I don't think I need this actually. Maybe I lied. Because we could use it lookup. Okay, so left node is equal to lookup of left index, right node is equal to lookup of right index, and they should be next to each other anyway, or left node dot next. So okay, so then we also want to remove right node dot index, and then technically something like this, if it exists, right? If next node dot next is not none, then we remove it from the heap. And this is just also, yeah, I don't know if this is worth recalculating, but that's fine. I don't think it's slow, but it's just annoying and easy to make typos on. I think that's the bigger part. Okay, so then we move that. Okay, and then now we move stuff from the heap. We are okay, right? Okay, now we're consistent with respect to the heap, and now we have to, yeah, I mean, I think that's fine. The heap is the hard part, right? So that means that, okay, so let's say we have the left node and the right node. Let's create a new node. Is equal to, what is my definition again? Node, we're going to keep the left node's index, just for whatever reason. And then the sum is going to be new x, right? Which hopefully it didn't change, so we don't have to recalculate. Okay, right? No, because we, I mean we could, but lookup has a reference to the node, so I think we don't have to have a new node. We just remove the next node, right? So left node dot row, we add right node dot row, and then now we want to remove it. So left node dot next is equal to right node dot next, and then right node dot next dot previous or prev is equal to left node. I think that's it actually. If right node dot next is not none, and then if right node dot next is not none, then we have to add a new thing to the heap, right? So that means that, oops, new thing to the heap, it's gonna be, what is it, left node dot value plus left node, oh no, plus, well, now it's left node as well, so it's fine. Left node dot next dot value, left node dot index, left node dot next dot index, right? And then we should, I mean that's fine, and we should be done, but we have to keep track of the total, which we haven't done. Okay, so also we have to keep track of the answer. We don't really use Q1 for this, but okay. Okay. I mean, I know this isn't right. I just want to make sure that this works to a degree, and not get a runtime error like this. Return. Oh, whoops. Whatever. We should never reference it. Actually, we only reference it in root.next anyway. Okay, so at least it terminates and doesn't create anything funky, right? Maybe. Yeah. Actually, I would like to print out sorted list just for fun. What do I call it? Heap. Okay. Okay, so it goes 5. Oh, this is after removal, so that's good. Okay, so for, what is this again? How is it sorted? Is sum, right? Oh, it's not adjacent. So it's 4, 5, 7. Okay, so I mean, I think, and then it goes to 5, 1. What do we remove? Oh, we remove this one, so there's no Oh, but we have to adjust the left sum now. Okay, so actually this is good because we have to remove the 5. We have to update the 5 as well. So we only did we update? Do we want to? How do we want to handle it? I mean, it's fine. That's why I wanted to check this because I wasn't confident about it. And we definitely caught it because we should not update this node in the heap, but we have to update the previous node, right? So okay, so yeah, okay, yeah. If left node dot previous, this is the only time where having it not none is a little bit in asymmetric, right? So we want to update previous sum, right? So here, yeah, do I keep track of the sum? I don't. Maybe I should. Maybe that's easier. Okay. Right, except for the last element. I guess that's a little bit awkward. Yeah, maybe not. I don't know. I think this introduced more variables I have to think about, more states. So okay, so the previous sum. I guess I have to track this, right? So okay, previous value is equal left node dot value. Okay, so update previous sum. So then now, previous. Okay, so left node dot previous dot value plus previous value is the old one, right? So we have to remove this one, left node dot previous dot index, left node dot index, right? And then now we want to add left node dot previous dot value plus this current value, the new added value, and then the rest should be the same. Okay, let's run it again. None is not. None object. Okay, so which one is none? This can't be none. Left node dot previous could be none, I suppose. But then why would it? Oh no, it's on the remove. That's expected, I suppose. But how can left node be? Oh, I don't set it to the root, do I? Current dot next dot previous is equal to current, right? So why wouldn't it? Am I silly? Maybe. It should never be none, is what I wanted to do. Yep. Oh, it's always none, in fact. Oh, I wrote previous instead of pref. I was inconsistent. I usually write previous out, that's why. Okay. Now this is better. Okay, so then now we went from... Okay, so we went to 4, and then now this 2 updates to a 6, and then it updates to a 7. Is that right? I guess so. This is 4, this is... and then 6. I think alternatively, you could have done this one with prefix sums. Now that I think about it, or like range prefix sum something, but like segments from left and right, and then prefix sum is the key. Yeah, whatever. It's too late. Or I'm already committed to this. How much time do I have left? 26 minutes. So I spent another 20 minutes on this, but or another 10 minutes. Okay, so why does this do? Is it 6? I mean, is it 11? I think 11 is wrong. Oh, no. It's not 7 plus 11. It's 5 plus 6. Okay, so I think this is right. Yeah. I don't know why this doesn't print another thingy. Oh, because it's on total, and total it's only on this, so that's why. Okay, that's fine. I was just kind of... Okay. I mean, it has to reduce at least once, but we want to... maybe the way that I did this is not super clean for keeping track of the number of inversions. I'm trying to think whether I can cheat and like, is there a data structure that just answers this for me? Plug in, like, can I use segment tree for this? Like query for the number of numbers bigger than X in a range or something. Maybe that's easier than keeping track of this, honestly. Okay, so it's range max. Yeah, so it's just range max, right? Because then, oh, range max and range min. So you have two segment trees, and then you update as you go, right? Maybe that's, yeah, maybe that's a little bit cleaner. Or it's just a little bit easier to not think about this. What is n again? N is 10 to the 5th, so maybe it's a little bit wonky, honestly. I think I can do it the other way, but I don't know. Let me find my segment tree thing. Okay. I mean, you could also you can also probably use a binary index tree. Is that would that be fast enough? I guess it'll be faster, but I haven't done it. Maybe not. I don't know. Okay, let's find my segment tree. Okay, so I have this, right? Is this right? This is probably right? I don't usually. I don't know. I feel like I usually have one that is. Okay. I mean, I don't know. Okay, fine. Okay. I think this is actually. I don't know if this is the cleanest way, but it would. No, you can't do it just that way. Hang on. I mean, it updates the current state and it updates that the partition, but then you have to check it for each number. So maybe this is wrong. Maybe I have to do it the other way. Okay. I don't. 21 minutes left. Okay, this is kind of sad, but I mean, of course, it goes out of bounds because this doesn't decrement. Okay, so we have to look at the previous states, right? So the previous states, we have left node, right? So, okay, so if left node is dot value is greater than right node dot value, then we already have one previous state, which is true, right? So here, if that's the case, okay, treat as remove and then add. Okay, fine. So if this is the case, then total subtract by 1, right? If left node dot previous is not root and left node dot previous dot value is greater than left node dot value, then total also subtract by 1, right? And then if right node dot value or dot next is not none, and right node dot value is greater than right node dot next dot value, then also total, right? Okay. But then now we have to add back, right? So here, now we have to add back. We have to add if left node dot previous is not equal to root, and left node dot previous dot value is greater than left node. I don't know why I didn't just copy paste this. Bring back 1, right? If left node dot next is not none, and left node dot value is greater than left node dot next dot value, and I have to type it correctly. Total, we add it back to 1. Okay, maybe this is good enough. Let's give it a try. Nope, 0 0 for some reason. Oh, I have to. This always I don't know. Okay, maybe that's fine. 2 0. Okay, that's actually better. Am I confident about this? No, but I have 20 minutes. That's getting into better wrong answer than anything kind of solution. So okay, but this is not great. So that probably means that our totals are not correct. So that's fine. Maybe fine is a debugging thing, right? So this total, we start with this 3. That truth, you have 2 greater than -1. Okay, let's just print it out then. Print total, the new total, and then we'll see. Okay. So okay, so you have 3 changes. We remove the total. Okay, so we remove the index at 4 and 5. Do I actually add this correctly? No. Okay, should be okay. I don't even use the right index really, right? But yeah, well, I guess I don't actually. Okay, so there's 3 inversions, a 2, -1, and yeah, 2, -1, -1, -2. Why do I have 3 then? That seems like it's just 1, right? Or 2, right? I mean, that may explain it, but I don't even know how that could be possible. That is the simplest part. Total. Okay, -1, -2. 2, -1, -1, -2. Why do I have total increment? Huh? Is that from a previous thing? Why is it 3? Okay, -1, -2. 2. Oh, I am dumb. Because current is on the root. I feel like this root has gotten me nothing. So, but also, I mean, it's fine. This should have been like a negative, really big number. Negative infinity, say. Okay, well. Okay, so it gives me 10. What is the expected answer? Oh no, on one-time errors, they don't tell you the expected answer. That is actually a little bit sad for my debugging. I don't know if this is the right answer. But 10, you basically eliminate the entire thing, right? So, yeah, also remember to remove this, right? All right, okay, let's go. I mean, I guess I could have ran a corrector to check whether that's correct, but okay. I mean, okay, so that was a silly mistake after all. Thanks for watching, everybody. Hit the like button, hit the subscribe button, join me in Discord. Let me know what you think about this problem, this contest, the explanation, everything in between. Stay good, stay healthy to good mental health. I'll see y'all later and take care. Bye-bye.